It would be really nice if we could see a sequence like this, where the nth term is 7 plus 1 over n, and say, hey, 7, this is just a constant sequence that converges to 7, and 1 over n is just a sequence that converges to 0, so this sequence that's made up of their sum must converge to 7 plus 0, or 7. That would save us the time of always having to write a proof from the definition that a sequence converges when it's just the sum of sequences we already know. But we don't actually know that convergent sequences behave in this nice way unless we can prove it. We'll prove that if an is a sequence converging to a and bn is a sequence converging to b, then the sequence defined like this, where the nth term is an plus bn, this sequence converges to the sum of the limits of an and bn, a plus b. Put more elegantly, the sum of convergent sequences converges to the sum of their limits. When we try to prove that an explicitly defined sequence converges to some limit, we typically begin with some scratch work, where we have the absolute value of a term of the sequence minus the limit, and we write that this is less than epsilon, and then we solve this for n, and we're able to construct our proof. But in this case, we don't have an explicitly defined sequence. Instead, we have an arbitrary sequence whose terms happen to equal the sum of the terms of two convergent sequences. To prove that a sequence like this converges, we begin with the same sort of absolute value expression. So we'll look at the absolute value of a term of our sequence, which is an plus bn minus the supposed limit. We would like the limit to be a plus b. We're hoping that's how this works, and we're trying to prove it. So we have minus a plus b in parentheses. In our proof that this sequence converges to this limit, we're going to want to show that this is less than epsilon eventually. So what we want to do now is focus on the things that we know we can make arbitrarily small. Because an converges to a, we know that we can make the absolute value of an minus a arbitrarily small, by definition of a convergent sequence. Similarly, we can make the absolute value of bn minus its limit b arbitrarily small. So the key is, if we can transform this expression into something consisting of this and this, then we might be able to make it too arbitrarily small. We may begin by distributing the negative, so we have that this is equal to the absolute value of an plus bn minus a minus b. And then, knowing the sort of expression that we can control, we might want to move the negative a over with an and move the negative b over with bn. Doing that, we have that this is equal to an minus a plus bn minus b. Putting these pieces in parentheses might make it clear now that using the triangle inequality is going to be a good idea. By the triangle inequality, the absolute value of the sum of two things is less than or equal to the sum of the absolute values of those things. And so we have that this is less than or equal to the absolute value of an minus a plus the absolute value of bn minus b. And now we're cooking. We've got our original expression, which is what we're going to need to prove something about. We've got that is less than or equal to the sum of two things that we can make arbitrarily small. We're going to want our proof to end with this sum being less than epsilon. That is, of course, after taking an arbitrary epsilon greater than 0. In order to ensure that this sum is less than epsilon, we'll want both of these terms in the sum to be less than half epsilon. Remember, after taking epsilon greater than 0 in a convergent sequence proof, we then set a value for big N that we think will work for our proof. So what value for big N will be big enough to ensure these two inequalities? Well, let's make this a little bit smaller and turn our attention over to the absolute value of an minus a and the absolute value of bn minus b. By definition of an converging to a, we know there exists a natural number big N1 so that every term of the sequence after the big N1th term is within epsilon over 2 of the limit a. Similarly, since Bn converges to B, we know there exists a natural number big N2 so that every term of the sequence after the big N2th term is within epsilon over 2 of the limit B. So to make our big N big enough to guarantee both of these inequalities, all we need to do is set big N equal to the maximum of big N1 and big N2. Let's do it. To really make the magic happen in our proof, we'll make this a little smaller, set it to the side, and bring this line down. So we set big N equal to the maximum of N1 and N2. Now, when we consider terms of our sequence after the big Nth term, we'll know that we have this inequality and this inequality guaranteed. Now we're basically just rewriting what we already wrote before in order to figure out how to construct this proof. We want to show that the distance between terms of our sequence and the supposed limit is less than epsilon. We distribute the negative, then rearrange the terms in the expression, then apply the triangle inequality, and now we're nearly there. N is greater than the maximum of big N1 and big N2, which means that N is greater than big N1 and N is greater than big N2. Thus, the absolute value of An minus A is less than epsilon over 2, and the absolute value of Bn minus B is less than epsilon over 2. So, by replacing both of these terms with epsilon over 2, we make the quantity bigger. So this is less than epsilon over 2 plus epsilon over 2. That, of course, is equal to epsilon. And so for an arbitrary positive epsilon, we found a number, big N, so that every term of our sequence after the big Nth term is within epsilon of A plus B. Thus, a sequence whose terms are comprised of the sum of the terms of two convergent sequences converges to the sum of the limits of those convergent sequences. If An converges to A and Bn converges to B, then An plus Bn converges to A plus B.